Okay, and also the screen recording software that I'm using is called Screencastify, although that's not the only one out there. It's quite good though because it allows you to save things straight onto YouTube if you have a YouTube channel for your notes or whatever. Some people make YouTube videos for homework. So, looking at Force's checklist, and basically, it's possible that this is just sort of a general checklist that they've rolled out every year, and in which case it's just going to cover the specification. It's just going to cover the syllabus that we've looked at just a moment ago. It hopefully will be written in a more student-friendly way so we can make sense of it. If it's got anything missing, I would suggest using the thing that they've given you here, this checklist we're looking at, because we're in weird circumstances where the schools are writing the tests. The schools wrote the tests and they wrote the tick sheet. So it's very unlikely that the tests and the tick sheet won't match. So let's have a quick look around this. I'll use some highlighters and some pens to identify what we've got here. When a force causes, and we've got some codes here, 5.2. I'm not sure what these codes are. Section, okay. I'm not sure if that is that a section in a textbook. Okay. Yeah. Okay. Probably, yeah, because the 5 will be P5, then 2, so it will be just section 2. Okay. When a force causes an object to move through a distance, so this one's talking about work. So basically what is work? Work is, and it talks about it over here as well, whenever there is an energy transfer, any energy transfer whatsoever, let's say a battery turns chemical energy into electrical energy, then we are saying that the battery is doing work. Okay, work is being done. And that's why work is measured in energy, measured in joules, because it is, and it's energy. It's a measure of energy. It's how much energy that has been transferred usefully. So that's what work is. Now, when you calculate work at GCSE, it's pretty much always mechanical work, and you don't calculate it. I mean, it's good to know that that's what it is, that it's the energy transfer. The way that you generally calculate it is with this formula down here, force times distance. So let's say I'm pushing a block. This is the most classic example. You push a block a certain distance. And then the work done, let's do WD, is equal to the force multiplied by the distance. However, there's a bit of confusion here because what's the energy transfer that's taken place then? It's a bit confusing because I've pushed a block. It doesn't. When the block's sitting still, there's no energy in it, and when I finish pushing it, the block's sitting still again. So what energy transfer has taken place? See if you can work it out. So when I pushed the block, there was I did some work where. Okay, we can understand that. We can also understand that energy must have been used because I'm slightly more tired after doing it. If I push blocks all day, I'd run out of energy. So we're familiar with the fact that energy has definitely got used. But what we would like to do here, to understand the topic better, is to identify what energy transfer took place. In other words, what was the starting energy? What was the final energy? Okay. So I'll give you a clue that kinetic is involved, but when the block was just sitting still, there was no energy there, was there? It wasn't moving, so there's no kinetic energy. And it hasn't moved upwards, so there's no gravitational energy gained either. If I pushed it up a slope, sure, the block has now got some gravitational energy because it's gained. And if it fell off the top, let's say if there was it came to a verge and it fell off, then we can see that there's proof that it has gravitational energy because that was, it would turn back into kinetic and crash into the ground. But if I'm just pushing it along the ground, and then I stop pushing it, then what's the energy before and what's the energy afterwards? So the other clue is that the way that I've framed the question is to deliberately catch you out. So it's there's not just the block didn't move on its own, did it? I pushed it. So I am involved in the system. Okay? So we've got to think about the energy that I have as well as the energy that the block has. And then at the end, the energy that I have and the energy that the block has. Okay? And think about what type of energy each one of us might have before, during, and afterwards. So where did I get my energy from to push the block? Right, okay, so the starting energy in this situation is chemical. Yeah, chemical energy being transferred into what? Into what? Yeah, kinetic, good. And then into what? Then it gets difficult again. Because it seems to have been into nothing. It's all gone. But we know that energy can't be created or destroyed, so that can't have happened. So the next question, maybe to get us to think about a little bit more about this, is why did the block stop? I didn't, if I, going back to forces, which I know that isn't on this anymore, but there was, there wasn't, I didn't stop it from moving. I pushed it forward, and when I stopped pushing it, it stopped moving. So, according to one of Newton's laws, it should have carried on moving at constant speed. So why didn't it? Why did it stop moving? Well, if it was on ice, it would probably stop moving a little bit less quickly. So what is it that's on? Why on ice? If I pushed it, one, I wouldn't have to push it as hard either, and also when I'd stop pushing it, it would carry on going for a little bit. Why is this? So it's because of friction. Okay, so friction is opposing my force, which is the reason why I have to push it so hard in the first place. So if I'm having to push a big heavy block across the ground, if there was no friction, it wouldn't be easy. It would be so easy. I could just push it with my little finger. It doesn't matter how heavy the object is because I'm not lifting it up. But if there's friction, it does matter how heavy the object is because the friction is actually affected by its weight. Now, what this means then, if there's friction, is that the energy that is being produced is heat or thermal energy. So when you are doing work, if you're in this example where you're pushing a block, and this is one that catches people out all the time. You see, it starts simple, and then you start asking probing questions, and people get stuck. The energy transfer was chemical to kinetic to heat. Or more accurately, it was chemical to kinetic and heat, and then from kinetic to heat. Because as it was going from chemical to kinetic, it was also producing heat at the same time. But if we ignore the first lot of heat, it's basically chemical to kinetic to heat. All right. So where's the energy at the end? Well, the box is now a tiny bit warmer. The air around it is a tiny bit warmer. The ground is a tiny bit warmer, and the energy gradually heats up everything else around it. And the word we want to be sort of etching into our mind is dissipate. The energy dissipates. So where does the energy go? Why is it's dissipated to the environment? So the way in which this gets caught out, the way in which people get caught out on this, is you have a let's have a look at an example. Do we have to do kinetic energy? And is kinetic energy in here? Let's have a quick look. Doesn't look like it is actually. Momentum. Okay. So we won't have to do. Okay, I won't talk about kinetic energy then. But if you're stopping a car, let's say you're using brakes to stop a car, it's the opposite way round to what to my situation. So I had a block and I was pushing it. This time I'm applying brakes to stop a car or to slow it down, eventually to make it come to a stop. Now, the opposing force of the brakes was actually going to be of the friction between the road and the tires and the brakes on the wheels. But if we know that if we can see that it takes this much distance, for it to come to a stop, 10 meters, the work done by the brakes is still going to be the same as force times distance. So it's just still going to be, and let's say F is equal to 500 newtons. So it might phrase a question like, how much energy was used, or how much thermal energy was produced by using the brakes, and the answer to that would be, or the energy transfer is going to be kinetic to thermal in this case, and it's going to be force times distance again, because we can use the same formula to convert, because that arrow essentially is the work done. And so the amount of thermal energy would have to have been 5,000 joules. Okay. So if we were doing kinetic energy, we could then calculate what the initial velocity was and stuff like this, but we're not going to do that. So let's go on then. 1 joule of work done is when a force of 1 Newton causes a displacement of 1. Displacement basically means the same as distance. The difference between displacement and distance is that if I walk forwards 1 meter or backwards 1 meter, the distance is still 1 meter, whereas displacement will be negative 1 meter for backwards. Okay. I'm simplifying, but that's gives you, that just that one sentence on its own will get you 90% of the marks, and we can look at the other 10% if we have time. Students should be able to convert between Newton meters and joules. Well, basically that's quite easy. 1 Newton meter is 1 joule. They're the same thing. All right. Work done against frictional forces acting on an object causes a rise in temperature of the object. Yes, because we're doing its energy transfer into thermal energy. If an object moves along a straight line, the distance traveled can be represented by a distance time graph. Okay, so this is okay. So we're looking at distance time graphs. I might look at that in a moment. Bring that back in a moment. We've got some quite good simulations to look at that. Speed of an object can be calculated from the gradient of a distance time graph. Okay, yeah. If an object is accelerating, its speed at any particular time can be determined by drawing a tangent measuring the gradient of a distance time graph. Yes. All right. We'll look at all these together in a moment. Distance time graphs. We'll come back to that one. Students should be able to draw distance time graphs from measurements and interpret lines of slopes. Okay. So you should be able to do speed from a distance time graph. This looks like a little bit of repetition here, so we'll look at that together in a moment. The average acceleration, I might pause my video for this a little bit. I'll just briefly mention that it says a change in velocity. If it was a decrease in velocity, then the change in velocity would be negative. So you could, rather than think about it as the change in velocity, you can think about it as the increase in velocity. An object that slows down is decelerating. Yeah. And generally speaking, deceleration would be a negative acceleration, but only generally speaking. It's more accurate to say that we have a direction. Let's say if we're talking about one dimension, like left and right, and I say that if I take an object and I'm saying the object is moving at 5 meters per second, right? And then I write down the velocity, let's say the starting velocity, u, is equal to 5 meters per second, right? Oh, come on. Now, because I've said that, I've now decided that right is positive. Okay, right is forwards. I could have said, because if I had another object, if we were looking at 2 objects, and that one went at 5 meters per second, it really struggles whenever I'm using a screen recording software. So let's say now that's 1, that's 2, and I would say U1 is 5 meters per second, but the second one I would have to actually say was negative 5 meters per second, right? So it's the direction that makes it positive or negative, not whether it's slowing down or speeding up. However, usually it will end up being the same. And I'll show you how you could get caught out by that. So in the if object 1 was getting faster, then the acceleration would be acting towards the right, and so the acceleration is positive, right? And if the object was slowing down, the acceleration would be acting towards the left, and so the acceleration would be negative, right? Now, if object 2 was speeding up, you can see actually the acceleration would not be positive because left is negative. So the acceleration in that case would be negative. So it's not about whether it's speeding up or slowing down that makes it positive or negative acceleration, although it does usually, but it's about whether or not the acceleration is forwards or backwards, whatever you consider to be forwards or backwards. And it's up to you. Usually right is positive and left is negative, but it's up to you as long as you're consistent with that question. Yeah, does that make sense? Okay, all right. So that's acceleration. We're going to do motion graphs in a moment. I just want to see what else we've got on this list. Acceleration object. So we've got a velocity time. This is why I didn't want to do it straight away, because I might do velocity time graphs and speed and distance time graphs together. This one, a lot of people get confused by this equation. It looks a bit weird. We've used Pythagoras in maths, right? So we know that in Pythagoras, it's a squared is equal to b squared plus c squared. And you know to square root your answer. So if we wanted to say what's equal to c, we wouldn't say we would do that, right? So it's just a matter of rearranging the formula in the same way. So as long as you're not confused, as long as you're able to do that, then that formula up here, v squared minus u squared equals 2as, that shouldn't confuse you. As long as you're familiar with how to rearrange that. Do you think you'd be able to rearrange that formula in all the different ways? Because otherwise we can give that a practice. Shall we give that a quick go? So we're going to go, we got v squared minus u squared. I'm going to write it down here. Equals 2as. We need to know that v is final velocity, u is initial velocity, a is acceleration, and s is displacement or distance. Well, displacement, yeah, we'll say it is displacement. And then you just got to know whether or not it's forwards or backwards. And then what we want to do is try to rearrange it for v is equal to, and u is equal to, and a is equal to, and s is equal to. So see if you can give me the version of the formula for each one of those. Okay, I'll just pause the video. Yeah, good. I'm fairly happy that you'll be able to rearrange those fine. I'm just conscious of time. I'm just trying to work out how we should spend the remaining minutes. So we've got looking at inertial mass. Students should be able to explain that inertial mass is a measure of how difficult it is to change the velocity of an object. Inertial mass is defined as a ratio of force over acceleration. Basically, it just means mass. But if we take the formula which they're using, F is equal to ma, then you rearrange it to say that m is equal to F over a. We can see it's the ratio of force over acceleration, so mass it can be thought of as a measure of how hard it is to accelerate something. So how hard it is to get something to start to speed up. And you can imagine that, right? Something really, really heavy, you start to push it and it hardly seems like it's moving at all at first. And then it just starts to gain speed. And likewise, if you wanted to slow something down that was very heavy, it would be very difficult for the same reason. So students should be able to estimate the speed, accelerations and forces involved in speeds, accelerations and forces involved in large accelerations for every day. Right, these ones there's gonna be some book that you can find. You need to sort of start to just memorize the values of things like walking speed, running speed, and things like that. You don't have to know the exact numbers, but you need to get a ballpark figure. So they may actually ask you so they'll get you to like calculate the speed of something like a car driving, and they might say, how does this compare with the average speed of somebody walking? And you which is I think they want you to kind of get an idea of how big numbers are and what speed, whether or not it's a fast speed or a slow speed. Students should recognize the use of a symbol that indicates an approximate value or approximate answer. We should be able to use the symbol that indicates an approximate value or an approximate answer. Sorry, let me just hang up on that person. So what this will probably be is, let's say if I'm trying to work out a value that A is roughly equal to 3, I can do that. All right? It's like a wiggly equal sign. Now there is another one, which is just one line, and I can't remember the differences apart from the single line is less precise than the double line. So I think it could be like the first one could, A could be somewhere between 4 and 5, whereas the top one, A would be somewhere between 2.9 and 3.2, right? So that's the kind of, this is like a ballpark figure. This is like, rounding it up, I guess. But you may need to double check that. That may be all you need to know. I'd be surprised if you need to know any more than that. But yeah, momentum is defined by the equation mass times velocity. We may not have a chance to look at momentum. I'm just trying to work out, should we look at momentum or should we look at? Let's dive into the what do you call it? The resource bank, and we can have a look at some simulations, and maybe we can look at a bit of momentum, a bit of motion graphs. Right. So let me just start recording again. And okay. So we've got, okay, what do we want to do? We want to go not to videos. By the way, you can probably find videos I made on motion graphs as well before, so check that out. But let's go to the simulations. I think a good one to start off with would be this one. But also, I'm going to open a couple other ones as well. Where is it? I think this one will be quite good too. And what else? Maybe we're going to open up that one as well. And we'll see if we can use momentum. Okay, I'll get that one going. We won't use it straight away. And let's look at this. Oh, okay. Can I actually, where's the simulation? Okay, cool. This looks good. So let's get an idea. This is going to be distance against time. So if I press play, okay. Let me just reset that. What do I have to do? Reset. Okay, I see. Right. So if I press play, we've got a car driving along. Nothing to. Oh, and then he stops for a little bit. Then he carries on driving. Right. Okay. So if you put some photos in there, it would look like that, right? If you took a photo every 1 second, they would look like that, yeah. And if you put some markers along, they would look like that. And if you joined up the markers, they would look like that, right? So this is a good way to see that clearly a flat line is not moving, and you can see that if it was going faster, it'd be steeper. So I don't know if we've got. Don't know if we can see that. There we go, he's going faster, then he slows down, and then he stops, right? And now what you can do with this as well is you can actually measure, so this is what they were talking about earlier on, you can actually measure this is distance. So you can measure the velocity by calculating the gradient. So in other words, if I looked at this first bit down here, we can see that from 0 to 3, the time was equal to 3 seconds, and he travelled over that period of time. He travelled a total of 100 meters. So I could work out the velocity by distance divided by time, and so it'd just be 100 over 3, right? Which is 33 meters per second rounded up. You could also do the average velocity by just doing from the start to the end. So just do a triangle all the way from the start to the end. That's very messy, but and this time we're looking at 10 t is equal to 10 seconds, and the total distance travelled is 140. So you do 140 divided by 10, so you travel an average of 14 meters per second. That is the average. Clearly, we can see the velocity changed, but we can work out for the bits where it's constant, we can work out the individual speeds using the same method, right? So that for that bit there, it was 33 meters per second. Now for this bit here, we would do, well, now it's increased from 100 to 140. So that's an increase of 40 meters over the course of 3 seconds. So it's going to be 40 over 3. So that's this time it's only going to be 10.3 meters per second. All right. What it'll say is so let's say we've got this graph here, and it says it will say between 2 points. If it says the whole journey, then you do what I've just done there. We did 140 over 10. Or it might say, if it says what's the exact speed at, say, this point here, let's say at 5 seconds, then you can do the gradient of that straight part of the line. If it was a curve, let's see if we can find a curve. No, that's not. Let's look at the later one, see if we've got a curve. Oh, they're not going to do it, are they, I bet? Okay, I can show you a curve in a moment. I don't know where it was now. Is it that one? Yeah. If it's a curve, then you draw a tangent, and I'll demonstrate that in a moment. But essentially, it's about. So I mean, even when I did the first one here, when I did 0 to 3 seconds, I did 100 meters, and I said the speed was 100 over 3, 33 meters per second. That is still the average speed between that point. We don't know if between each second he speeded up and slowed down, and then do you know what I mean? So he could have speeded up, slowed down, speeded up, slowed down, speeded up, slowed down. But because we only took measurements every second, and we don't know that, we just assume that he travelled at the same speed between second 1, second 2, second 3, right? So if I only took a measurement at 0 second and at 10 second, I would just get a straight line. And if I join them up, I'd get a straight line like that. Okay. So, anyway, so I wanted to demonstrate how to relate this to distance to a speed time graph. Let's just have a look at that. I'll just clear my screen. And this animation is quite good. It helps you to compare the two. So compare all of them. So, right. Maybe it's not this one that I want actually. I'm just going to pause my video again for a moment. Right. Yeah. So with this one, let's start off by just looking at a velocity time graph. So velocity time graph, well, let's just make it positive to start off with. Velocity is constant, and then it accelerates, and then it's constant again. If it was staying still, it'd be like this, right? It slowed down, and then it wasn't moving anymore. So what we can do is we could look at how would this be represented in a position versus time. So you click that, and that's what it would look like. So it's constant at the beginning. When it slows down, it starts to smooth out. And then when it's flat, it goes. When it starts to 0, it goes flat on the distance time graph. You can also look. Sorry, say again. Constant. So let's make it flat. If it's totally flat, then that means the velocity is constant the whole time, right? And so the velocity is not changing, or the speed is not changing. If it was a higher speed, I'm going to have to move them all up one by one. In fact, let me just to reduce confusion, I'll just turn that off. Hopefully that will reduce confusion. And let's move all that to that. And you can see it's steeper, but it's still a straight line, right? So the straight line, if it's a constant velocity. Now, if we get a curve in a position time graph, or in other words, a distance time graph, if the velocity changes. So I'll show you. You can see now there's a curve. Let's imagine I had a constant increase in velocity. Then it curves up because the steepness is changing. The velocity is represented in the distance time graph by how steep it is. If the velocity is getting higher, then the distance time graph is getting steeper, and so it's curving upwards. Likewise, if I started off at a high speed and I started to decrease, well, unfortunately, it's gone off the thing. Can we zoom out? Okay. Let's start off a lot lower. Right, hopefully you can see what I'm kind of trying to demonstrate. That so it curves the other way when the velocity is reducing. Now you can actually work out the distance traveled from a velocity time graph by calculating the area. The area underneath a distance time graph tells you nothing. Okay, we might tell you something actually, but nothing that you need to know about, and nothing that I can think of. But yeah, so for a distance time graph, you can measure the gradient, and you can measure the gradient at different points. So that's what I was going to demonstrate, wasn't it? I was going to look at measuring the gradient, a tangent. So what about if we have the steepness is changing, like here? What would be the speed at this point? We can see it's slowing down, and eventually it stops. What would it be here? So what you do is you draw a line. It's going to be difficult for me to draw it on this, but I'll do my best. You want to get it so as it sort of just touches the edge, and it's tangents are quite difficult to draw, but that's about right. And then what you would do with that tangent is do the gradient of the tangent. Okay, now the gradient of the tangent would give you the speed of the object where the tangent is touching the line, because what the tangent is a way of showing what the steepness of that line is. We can't, of course, do a gradient of a tiny point, so we make the tangent. All the tangent is making the point longer, so we have some more space to play with, and then we can actually work out the gradient of that line. So once again, sorry, go on. What were you going to say? The bigger the triangle, the better, always. However, sometimes it's not convenient. Okay, so bigger the triangle. In general, the bigger the triangle. The only reason I would not pick the biggest triangle sometimes is because the numbers are awkward. And so we want to get as big a triangle as possible where the numbers are easy enough and we can be fairly confident about the values that we're reading. Other than that, you want to make as big a triangle as possible. So with this tangent, because it's just my own line, I would just draw it all the way from one end to the other, and then just measure the triangle for the whole triangle for the whole line, providing I can get a good reading on the graph. So the gradient of a velocity time graph will give you the acceleration. If it's a downward slope, then you're going to get a negative number. So it's decelerating, of course. But and of course we can have a negative, right? And then we have a position time graph or displacement time graph, and it actually goes down. In fact, if it goes too far down, it can go back, go beyond, behind the point it originally started, right? You'd work out the gradient in the same way in all the cases, and it's just going to be the change in distance over time. In this case, it would be change in velocity over time. So the change in distance over time is the velocity. The change in velocity over time is the acceleration. Okay, so I'll just save that now.